everyone, thank you for coming for my talk. My name is Chen Haoxie from Pacific Northwest National Lab. Today I will talk in my work, Fast and Scalable Sparse Triangular Solver for multi-GPU based HPC architecture. Following the development of interconnect technology, multi-graphic processing units based services such as NVIDIA DGX1 and DGX2 are becoming increasingly popular in modern HPC systems to enhance the performance of high-throughput workloads such as the big data analysis and plus-scale applications. As this slide shows, the multi-GPU interconnect has developed from the PCIe to the NVMe switch, and such kind of multi-GPU systems has widely used in HPC systems and supercomputing systems. In this work, we try to achieve fast and scalable sparse triangular solver on a single node multiple GPU system. SpTrsv is considered as a main kernel for many important HPC applications such as power grid simulations. Given the low triangular sparse matrix or the upper triangular sparse matrix, SpTrsv is seeking the solution for the vector x, which we call each x is a component. As this picture shows, to solving the components, SpTrsv needs to satisfy the dependency. As a result, SpTrsv is inherent sequentially. For example, component 2 has to waiting for component 1 to finish, and component 3 has to waiting for component 0. Means that all 4 cores cannot work in parallel. Currently, there are two kinds of SpTrsv on GPUs. The first one is called level set SpTrsv. The basic idea is some components are independent and can be processed simultaneously. So they first analyze the matrix and then generates the level set for each group of components. This kind of analysis causes significant overhead and requires synchronization across levels. The second kind of SpTrsv is called synchronization-free SpTrsv. The basic idea is migrating the level set analysis at runtime, so the components are scheduled by the hardware warp switch of the GPUs. However, in this kind of approach, they need to data communication and updates, atomic updates, which causes too much overhead on the multiple GPU systems. In our work, we propose zero-copy SpTrsv for multiple GPU platforms. We leverage the new NVSHMEM technologies to design an efficient and scalable algorithm for SpTrsv kernels execution on single nodes multiple GPU systems. We achieve efficiency and asynchronous data communication using NVSHMEM. And to achieve better workload balance, we propose a task-based workload balance approach to ensure that the parallel components can be scheduled on different GPUs. This slide shows the agenda of my talk. I just finished motivation and introduction. Next, I will go to the detailed technologies for our zero-copy SpTrsv and show the evaluation result and the conclusion of my talk. Before I go to the detail of SpTrsv using NVSHMEM, we first developed SpTrsv using the unified memories. The advantage of unified memory is that it is very conventional to develop the algorithms, since it heightens the complexity for the users, and it relies on the page fault mechanisms, which achieves the cross-grain data copy through the GPUs. This picture shows the implementation of SpTrsv on unified memory systems. From this picture, we can see two features which limit the performance of SpTrsv in unified memories. First, the system-wide atomic update will access the data allocated on the unified memories from different GPUs simultaneously, resulting in data contention and page fault. Second, we can see that system-wide dependencies are unidirectional, which cause lower workload balances and limited the performance of GPU systems. So we conclude that the SpTrsv require low overhead and frequent communications. To overcome the bottleneck of unified memory, we consider using CUDA NVSHMEM to replace the communication channels. The CUDA NVSHMEM is an open SHMEM-based global programming interface for multiple GPUs. It allows GPU threads to access distributed memories through the data movement APIs, and it builds a directly load and stores, and builds the P2P communications between GPUs. The advantage of HPC is that it provides a high concurrent frame-rate message passing through the GPUs, and is able to achieve asynchronously one-sided data communications. We then use NVSHMEM to solve the data dependency update for SpTrsv. We convert the system-wide atomic update from unified memories to NVSHMEM shared memory spaces. This left shows the code algorithm we designed and how we mapping the data into the shared memory. As the red box shows, we propose a read-only inter-GPU communication model to parallelly collect all system-wide data asynchronously in multi-threads. And in this approach, we only has the device with atomic updates, which has much lower overhead compared to the system-wide atomic update. And compared to the unified memory approach, we isolate the execution for each GPUs and avoid page copy cost from the data contention and system-wide synchronization. Next, I will introduce the workload balance approach in our work across the multiple GPU systems. There are three kinds of approach: the balance components, balance non-zero values, and components ready robust, as this picture shows. In our experience, we observe the component ready robust achieves the better workload balance by ensuring that the parallel components are scheduled on different GPUs. However, schedule each component independently increase kernel launch overhead. So we propose the task-based workload distributions. We first group the component into tasks and schedule the tasks across GPUs. We also observe there is a trade-off for the task size. More tasks per GPU cause more balance. However, it also allows the localities for better performance within the tasks to using the shared memory. I just finished the detailed technologies for our zero-copy SpTrsv. Next, I will show the evaluation and the results and the conclusion my talk. We evaluate the SpTrsv on two multiple GPU systems, Water 100 DGX1 and Water 100 DGX2. Compared to the two systems, the major difference is the connection topologies. The DGX1 using a cube to connect the old nodes, point to point. However, the DGX2 using the NVS switches, so it achieves all GPU P2P connected through the switches. In our experiments, we choose 14 sparse metrics from switch Sparse, and two of them are out-of-memory metrics which cannot be allocated into one GPUs. We observe the intermediate areas only consumes 10% of total memory requirements. This slide shows the performance results by comparing with the HPC approach with the unified memory approach. We can the top one shows the comparison results on the DGX1s across different mechanisms. And the bottom one shows the conversations between the DGX1 and DGX systems and compared to the unified memories. And the result shows our design achieves average of 3.53 times speed up on DGX1 system and 3.60 times speed up on DGX2 systems with 4 GPUs over the unified memory designs. And this slide shows the SpTrsv result for the scalabilities. The left one shows the DGX1 result and the right one shows the DGX2 results. For DGX2 results, we can scale up to 16 GPUs. The results are normalized to the cool Sparse lab on single GPUs. And from these pictures, we can see the scalability depends on both matrix parallelisms and hardware structures. Next, I will conclude my talk. Through performance characterizations, we identify that applying the state-of-art unified memory for data sharing among GPUs may cause server performance penalty for SpTrsv. We leverage the new NVSHMEM technology to design an efficient and scalable algorithm for the SpTrsv kernels execution on multiple GPU systems. For better workload balance, we introduce a text-based workload distribution schemes. We demonstrate that the performance benefits and scalability of our approach SpTrsv designs a range of inputs that require out-of-core executions. Thank you for listening. Now I'm open for questions.